So everybody else is ready as
Hello,
well?
everybody. For me, it's okay also.
Okay, so in that case, let me just start. Thank you very much for this opportunity. I haven't given one of these truly global seminars for a while, but I'm happy to talk about this particular result. It's mainly based on recent joint work with Aleksis Vuoksenmaa, who just defended his thesis here in Helsinki a while ago. But it's also based on earlier work with Matteo Marcozzi in particular, but also with something which we have been doing and are doing with Sakari Pirnes, who is another PhD student here, Herbert Spohn, who you most know from München, and Alessia Notte from Italy, from GSSI. And the topic is generation of chaos in the cumulant hierarchy of the stochastic cuts model. Since it's a probability and stochastic seminar, I will try to focus on those things, even though, as you well know, I'm not an either. But what was motivating this particular work? It's really a lot of activity in the field of understanding the mathematical foundations of kinetic theory. And there have been two separate lines which look distinct, but not really are not. In fact, there's a lot of structural similarity. First of them was something I've been myself working quite a lot on nonlinear Schrödinger equation. I was working with Herbert Spohn on the discrete version of that, but there are a lot of nice results, especially by Deng and Hani, several papers on this topic where they use perturbation techniques to analyze these properties and prove these properties based on earlier work of Buckmaster, Sherman, and Shatta, for instance, also other names which didn't fit on the slide. And in particular, I wanted to mention Staffelani and Tran, Ambatsagolo and Kolo, Sherman, this type of people who you should keep in mind when you think about where all these techniques are coming from. There's another field that the second topic for kinetic theory, derivation of kinetic theory, understanding kinetic theory, and that's really the original one, starting from Boltzmann. That's what is called rarefied gas these days. I think of it as a billiard ball model. And it's elastic collisions between billiard balls. That's what it's about. And also there, as I said, there are connections between these things, these techniques, these questions, and the techniques of Deng and Hani. They, together with Ma, they managed to implement the analysis classification scheme also in the case of the perturbation expansion of the standard Boltzmann. But there are, of course, a lot of earlier works I should mention there. Lanford, Cengeniani, for instance, and of course, Bodino, Gallagher, Sanremo, Pulverenti, and Sergio Simonella as well, who come to my mind at the moment. And it's actually the second topic I'm focusing on today. And in fact, not on that particular one, it's too hard, but on a simplified version of that. And my topic somehow is I like to think of it as probability question. It's really a question what is behind in all of these cases? What is the key of understanding what's going on? So let me do a little bit of drawing. So thinking of the billiard balls. So in the original Boltzmann model, that's the case 2 above. There was a particle 1, that's a billiard ball 1, and it doesn't look like a ball here, but don't worry, which has a velocity v1, moving usually in 3 dimensions, but my picture is obviously in 2. And it's colliding with particle 2, which has velocity v2. These two particles, if they meet, they collide. They have an elastic collision, so time goes on. And afterwards, the velocities of these particles, let's say they are v1 prime and v2 prime. And when you derive the Boltzmann equation, in order to get to the Boltzmann equation, you actually need to assume essentially that you can take v1 and v2, let's say they are 3-dimensional velocity vectors, as independent random variables. That's what is nowadays called maybe Stochastic ansatz, or chaos simply. And that's the type of chaos which I mean in my title. So when I talk about chaos, in this talk, I mean chaos as statistical independence. In this particular case, it's the statistical independence of the incoming velocities. And everybody who has worked on this knows that this is a very nice assumption that all the incoming velocities before collisions are statistically independent. Of course, it cannot be true as soon as there are more than one collision, because you can never guarantee that these particles, so these velocities here, will then no longer be statistically independent. So they will be correlated, they will have dependence. And therefore the assumption, if you think of the joint distribution, it is spoiled at the first collision. So that's not something you are really allowed to assume. So chaos as statistical independence is behind Boltzmann equation, but you cannot assume it to be exactly true. And that's the key difficulty in this question. So since it cannot be exactly true, what do you then prove? So you have to prove propagation of approximate independence. And what does that even mean? How do you control things which are not exactly independent, but roughly independent, approximately independent? And as I said, even if the initial state, you can assume anything you like from the initial state in mathematics. So let's assume everything is independent. It doesn't hold anymore after first collision. And the method in this fairly lengthy analysis is to show that this you need to have some way of controlling this generation of independence. Actually, it's the generation of dependence which is the problem here. And you need to show that somehow an almost factorization property, in this case of, let's say, of velocity moments, will hold. And in order to control this, you have to do some fairly exact analysis, and this is often done by moment hierarchies, like BBGKY hierarchy. And one of the points of this talk is to show that cumulants can do better, or easier, at least in the model we are looking at. I think it's fair to say that cumulants will do a job easier. But to summarize a little bit what I'm talking about here. So chaos in kinetic theory, that's the topic. So that's some kind of statistical independence, and it will never be exact. It's always approximate statistical independence of the main involving quantities. So it could be velocities, and later on, in fact, it will be the kinetic energies of the particles, whose independence is sort of importance to us. I talk about propagation of chaos. The propagation part is the one which I mentioned before. If you start sufficiently independent, then you are supposed to remain that at least up to kinetic time. So kinetic theory holds at a certain time scale, and at least up to that time scale, you want this property to be preserved. Since that's behind your kinetic equation. The other topic for today is generation of chaos, and this is somehow harder, in the sense that even if you don't assume independence in the beginning, will it be generated? That question is quite tough in the case where the dynamics is deterministic, like in the nonlinear Schrödinger equation, let's say. It's also too hard for us at the moment for the billiard ball model. But fortunately, there was something simpler which was suggested to us where we can prove also the second property. But before going there, I'm afraid I have to introduce to you the main tools. So I already mentioned cumulants, and what we did analyze and what we proved with Aleksis in our recent preprint was a study of the time evolution over a cumulant hierarchy. So that's a collection of evolution equations involving cumulants. And almost as a byproduct, it's not completely mandatory, but certainly for us, it was greatly simplifying to use weak polynomials, so-called weak polynomials, to help in the proof, to simplify the proof. So I wanted to sort of introduce both. So why cumulants? So our key hypothesis here is that the smallness of joint cumulants is actually a good measure for almost independencies. Again, we are dealing with things which are not completely independent. They are almost independent. How do you measure that? We use cumulants for this purpose. And the reason why we think it's a good measure is that, just to recall, so for independent random variables y and z, the moments factorize, while if you have non-trivial cumulant involving both of these random variables, the corresponding cumulant will be exactly 0. And this will hold even in the more general case. So if you have small n random variables y1 to yn, and any one of these random variables in the joint distribution is independent from the rest. Well, for moments, then we would have an identity here in this factorization property. But for cumulants, this will turn into a question of that being 0. So it will imply that this particular cumulant of these variables is exactly 0. And again, following the same idea, almost independence, even in this case, should be somehow visible or measurable or controllable by smallness of these cumulants. And unfortunately, I just have to do the definitions next. So I'm giving you the generating function definitions, even though they certainly are maybe not the most convenient and certainly not the most general, because they assume the existence of generating functions. In our proof, we didn't have to worry about this point because of we have bounded random variables, so everything is analytic even for us. So all these derivatives make perfect sense. But just to make one particular calculation, let me use the generating functions just to introduce this. So just to remind you, so this expectation of the exponential is a generating function. By differentiating that, I get corresponding moments. And one of the things with dealing with this enormous numbers of random variables as we do is to find good notations. And the ones I'm having in this slide are from our paper with Matteo. So this particular moment-looking product means actually a real random variable which you obtain by multiplying these guys. The lower index, very similar looking, is something which you can think of as a sequence of random variables. It's mainly used in a little bit bad notation here. It's used to denote the arguments for the cumulant. Otherwise, that's a bit tough to write. And the derivatives follow the rule of the moments if you want. And the reason why I wanted to introduce weak polynomials at this stage already is that if you now think of something where there's a deterministic time evolution. So take a random variable with some random initial data for y, and any deterministic, let's say, given by some flow, some derivative equation for the time evolution, that makes yt as well a random variable, if the initial data is that. And now you can ask the question about the time derivative of the cumulant of these random variables. And indeed, if you follow this particular rule here in the definition, that's the same as, and then you assume that you have enough regularity to swap the order of the differentials. What you end up with to think about is the time derivative of the generating function. And this, by the chain rule, sorry, this is m like moment. So derivative of gc is derivative of log of gm is the same as this particular one just by chain rule. And now you think about differentiating here. So you take the derivative inside. What drops down is this term inside the expectation. But we are still left with this exponential divided by gm. And this is my notation for GW. So this guy here, evaluated at this particular random variable, or function of random variable, is what you will be left over after you differentiated the cumulant generating function. And why is this important? That function is so-called generating function for weak polynomials. This is the reason why they almost always arise when I want to look at evolution of cumulants. Because now I still have to do these derivatives here. And now you think about using Leibniz rule for this product of two functions here. You notice that this particular one is a linear function in eta. You can only differentiate it once. And if you sit down and do a calculation, you will get the sum over all the arguments inside the original cumulant. That's the L here. Those are the indices here. You sum over then. You take an expectation where you have this at the moment unknown derivative. I said that I don't tell you it's what it is. It's just deterministic. So this exists. Usually it's a function of yt itself. That would be the case for Hamiltonian evolution, for instance. But in any case, this is just a new random variable. But you need to compute the expectation of this new random variable with respect to the derivatives of this one, and they are always weak polynomials. And that's a mechanism in which weak polynomials sort of almost automatically arise when you look at the time evolution of cumulants. And the weak polynomial is defined by the same rule as for the other guys, just totally analogously, so you have to differentiate with the generating function with respect to eta. The trouble in the notation is that I should stress this a little bit. So this big polynomial notation is terrible. It looks like a power. It isn't. It is actually a polynomial. It's a polynomial of what? It's a polynomial of these y's, components of this. That's a collection of random variables. So it's a polynomial of the absorption of random variables. Its maximal order is denoted here. So this collection of variables is the maximal order for the big polynomial, but the coefficients are depending on the distribution of these random variables. So if you start to do the calculations here, so this guy here is in fact the exponential to minus GC, the generating function for the cumulants. And that property makes it both useful and hard to use, because as soon as you go beyond 2, explicit formulas are a little bit difficult to combine. And in fact, explicit formulas are often not needed even. Just to mention very quickly, one case when these big polynomials are easy, that's for the Gaussian case. So that's in fact the case when they were first introduced, because in the Gaussian case, my generating function turns into something which is exponential over second order polynomial. And that's helpful. It's helpful because that's in fact a generating function for Hermite polynomials. And for the Gaussian case, the big polynomials are Hermite polynomials. And in fact, cumulants are 0 starting from 3. And another thing you can check from these formulas. These protocol properties have been used before. We are not relying on these chaos expansions as such. We are rather, I'm thinking of these as big polynomials, as a regularized polynomial. That's the way I want to sort of use it. Why are they regularizing things? In order to turn, I wanted to have a cumulant hierarchy. So I have to do something for the final remaining expectation value in my formula. And indeed, the existence of big polynomials inside this expectation is useful. So without the regularization, so if I would have just a collection of labels in J and J prime, this would turn into the usual moments to cumulants formula, where this sum is enormous. I mean, it's a sum over all partitions of this joint index set. But the big polynomials reduce the number of terms in this sum. So they regularize this expression in a way that whenever you have a cluster in your partition which is completely inside the regularized part, those terms never appear in the sum. And this regularization can be quite a lot, depending on what the J prime is. And indeed, there's a formula where the more you add things here, the more regularization you get. But the combinator starts to get a bit heavy at this point. Anyway, that's the way how you end up with the cumulant hierarchy usually, because when you do the derivative on the left-hand side of a cumulant, using this formula, you end up with a rather complicated nonlinear term, typically nonlinear term involving the lower order cumulants. Just again reminding you, so this is a partition that the A is a cluster from the partition. So these are indeed lower order than the original index set, unless it's the full set. Okay, so that was my introduction to the techniques. These notations will appear now that we start to talk about it, but let's go to some stochastic models next. So the reason why the analysis is easier, let's say the probabilistic reason, is that it's sort of, I guess, understandable, believable, that when you introduce the highly mixing stochastic collisions, more mixing than the original one, you should help in making things more independent. That sounds reasonable. At least it was reasonable to Mark Katz, and it was equally reasonable to Clement Moore, who is the one who suggested this whole change to us. So I was meeting him at the workshop, and I explained our idea of trying to look at cumulant hierarchies. He was interested, but he was sort of, as well as we are, daunted by the complexity of this whole thing. And he suggested that we should try it first in the model where everything should be better known and better controlled. And this is indeed the stochastic Katz model he suggested. And his suggestion turned out to be better than I expected, truth be told. So that's an old model introduced by Mark Katz in '56. And he used it as a toy model to derive and understand Boltzmann equation. Understanding, well, I mean, it has a little bit too much stochasticity to be and no spatial dependence. It's a mean field model, so it lacks many of the features of the actual Boltzmann equation, but it's still it has the right path for having collision terms in the way of ordinary Boltzmann term. So it's a capital N particle system. So I'm going to keep this notation where capital N is the number of particles which collide, and small n will be counting the degrees of freedom which I'm interested in. So it's an order of cumulant, the small n. He was interested in physics, so he wanted to have three-dimensional collisions. We have too many indices already, so we dropped to one, and so do most mathematicians. So we look at the one-dimensional velocities only, just to simplify. There are also differences, most likely, but certainly for this talk, all the velocities from now on will be one-dimensional. So particles will move in one dimension. And the only thing we are interested, this is a mean field model, and we assume that the velocities decouple from their position. That's obviously not such a great assumption in real gas, but for the purposes of this derivation, let's make it. So the only degrees of freedom we are interested in is the velocity, which is now a real, so one-dimensional vector, meaning real random variable, and we denote them by VI. They are random even if they are deterministic in the beginning, because they collide random using a random collision rule. The rule is that there's a Poisson clock ticking, and once the clock rings, pick randomly a pair of particles, and this pair is uniformly distributed, and that gives it the mean field character. So there is no structure. The particles don't know who is next to them. You just pick any two of them. These two particles with labels I and j will collide. So these I and j are now randomly picked from the collection, a pair. And then you rotate this two-dimensional vector. So VI, Vj is now a two vector. You make a two-dimensional rotation by an angle theta to this two vector, and the formula here is still in this. And what is random here is the angle. We take the angle for simplicity again. We take the angle to be uniformly distributed for the computations in what we did with Aleksis. And this rotation is therefore given by this 2x2 rotation matrix Rij theta, which is random. Why rotations? There's one thing which we want to preserve from the original physical billiard ball collision. So we want that after the collision, or during the collision, the total energy of these particles will not change. And total energy is sum of Vij squared, which means that the length must be preserved. So the length of this random vector has to be preserved, and will be preserved by this two-dimensional collision. And that's a conservation law. So this is not totally mixing. There will be one conservation law. And indeed, if I will start it from a certain fixed value for the total energy, and therefore the evolution will always keep this total energy the same. So we will start with the total energy which has density 1, which means that the length which has the square root is square root of n, because there are n particles, each on average with energy 1, so that it is square root of n, which we want to do there. And in fact, also already Mark cuts this. And the conservation law is that even though this is random rotation of a very large vector, it always remains on the sphere defined above them. The transition operator for this guy is Q, and most of the work here has been starting with a density with respect to uniform probability measure on the sphere. So this means that for most of the work, you start with a fixed energy density, and then you let it evolve randomly, and then this density will be kept as a density, and yeah, therefore you will have an evolution equation for the density f small ft. We are also interested in more general cases. So this capital Ft is a measure. It has support on the sphere, but it doesn't need to be absolutely continuous with respect to the uniform. That's one thing which we can allow to change. As I said, the collision times are Poisson. So here's the formula for the evolution of the density. Let me not go into that. That's sort of Markov things. That's the evolution equation. So that's a generator for the densities. And what Katz did in 56, he assumed that the initial densities are chaotic now, as quotation marks. What he assumed is that they are close to a total product. They cannot be completely product because they have to remain on the sphere. but he proved that they remain chaotic. So he did prove propagation of chaos in that sense for that model. And he showed that the first marginal of this time-evolved things, when n number of particles goes to infinity, goes to some function. That's a function of v. That's a density of one. That's a density of the one particle marginal. Therefore, it's a density in R that satisfies this particular evolution equation here. And that's pretty close to standard Boltzmann, spatially homogeneous Boltzmann equation. The F0v here is the limit of the marginal of F0n. So there's an assumption going on here. Namely, you can't take any sequence of initial data, even if it's product, it has to have somehow a convergent marginal. That's something which you need to assume. The R theta in this formula, these primes are just like in my first drawing. So this is, you can think of this as before and after collision. The primes are the rotated ones. What do we know about this model? We know that it has been proven already before us that the density equilibrates. So F goes to 1. So the measure the n particle joint measure goes to uniform. That's mu n. It can be quantified. There's a spectral gap. The size of the spectral gap is also known. That's Carlin-Carvalho loss in 2003. And therefore, we have an estimate for the convergence of the density to uniform. It's exponentially fast. The trouble with this formula is that number here is almost never small. In particular, it's not small for the cuts type of things usually. It's not only small, it's huge. It's e to the capital N. And that's the reason why this formula is not as good as you would believe. It probably says the best possible thing. So it says that if you look at all n particles and you ask for all possible observables, that's the best you can do. So all possible initial data, also all possible observables. This is your convergence rate. It can be as bad as order of capital N. So this formula, this right-hand side goes to 0, becomes smaller than 1, let's say, at the order which can be as large as capital N. Indeed, this was tried to see if this is a fact. Can you, for instance, use relative entropy methods, entropy production techniques to show it's better? Well, the answer is that you can use it to study this, but it doesn't help you. If you allow, again, for all generality, you can go as bad as capital N. And in the paper of Michelin and Moore in 2013, they sort of studied this question extensively. So that maybe is the sort of most recent collection of results. These results assume a permutation invariant initial state. Let me speed up a little bit. So I think computations will become impossible in the remaining time. So just to mention what we did. So that's what was done before. We were now looking at cumulants, and we were looking at lower order cumulants. So our goal never was to look at cumulants which have a very large order. We always were thinking of results where you look at the first fixed, let's say, 5 cumulants. If you have computed cumulants, you already will be happy to be able to say anything about, let's say, 4th order cumulants. We turn this system around. So now we take this evolution equation for densities and turn it to evolution equation for observables. And this is exactly the trick which allows us to look at measures, more general measures as initial data. We are not looking at VI as our dynamical variable. We are looking at the energies, as I said, which are squares of this. So those are non-negative random variables. And the reason why they are helpful is that they satisfy this linear conservation law. So this one conservation law, the fact that you remain on the energy sphere, is for EIs, it's a law that the sum of these random variables is capital N. So it's a non-random random variable. So it's a deterministic random variable. What the price we pay is that even though the V's are expected to go to Gaussian, these E's will not. So they will satisfy some chi-squared distribution in the end. And how do we measure? I said that we measure chaoticity. So now we do measure it in a very quantitative way. And this was the final outcome, what we could do with Aleksis. So think of the left-hand side as these are energy cumulants. So E is energy here. R is just some collection of variables. Because of the permutation invariance, exchangeability, you don't need to you only need to focus on how many different random variables you have. That's something which we'll talk about more later. But in any case, think of the left-hand side as any cumulant. And this 0 here is time. So this is time 0 cumulant, or which has n small n variables and capital N in the big scheme of things. So we are looking at small n variables out of the capital N. And we assume from the initial state a bound which looks a bit arbitrary maybe in the beginning. So there's this usual factor which is associated with cumulants. That comes very often from combinatorics. So I would be surprised to see something much better than this. The important part of this bound is the dependence on capital N. So this B here is not allowed to depend on N if you want it, or if N, capital N is fixed, this B here should not be too large. That's part of the story here. And this N factor here has two control parameters. They are called C and alpha. The C is controlling degree of chaos, if you want. That's the way it will end up in the end. So C is a number which turns out to be that we can choose it between 0 and 1. The larger it is, the less chaotic your state is. So C equals 0 is something which we call a chaotic state. The alpha is a control parameter for doing the computations. It would be nice to do this for alpha equals 1, but it was not something we could do. So this alpha here is to sacrifice a little bit of logarithm. You can think of it like that. And for this reason, you can also think that it's close to 1, something over half. If you want to fix it, think over half. The important part is that if you look at this guy here, the factor is, if you write it in some more readable form, this is 1 over capital N to the power, that's positive, times something which is what we call the length of the R. That's the number of different labels in this label sequence R here on the left-hand side. So it counts how many different labels you have put here. So how many different energies. So there can be repetitions on the left-hand side, that's fine. But we are counting in the length how many different ones there are. If there is only one, then this doesn't do anything. So as I said, it's independence of E's. And if you have only one E, independence doesn't tell you anything. So, and indeed, this factor becomes active only when you have 2. But then as soon as you add a new random variable, it decreases the size of this kappa by a factor of 1 over n to the alpha. So for each new variable, n to the alpha. Okay. And I said that it looks ugly. In fact, it's not too bad. So we also proved that if you have any symmetric state, so if your particle labels, capital N particle labels are exchangeable, a symmetric state, which you can also generate if you want by looking at symmetrized observables, we can always find a bound of this type with C equals 1 and let's say alpha 1/2. And I talked about the B, that the B cannot be too large. In fact, B equals 4 is fine. So you can think of B as 4 if you want. You can think of C as 1. This includes even completely deterministic initial data, which have been symmetrized. The symmetrization is an important part of this calculation. And also one other thing, this exact bound holds only up to capital N over 2 labels. So once you have too many labels in this sequence, you are starting to see the constraint that you undersphere too much. So, and we never thought about going that high. So for us, the small n was always going to be, let's say, 10. And at capital N is going to infinity. So we didn't worry about the higher ones, but we were already happy with this one, that up to such a high order, we can control the initial cumulants of any initial data using such as this type of formulas. As you notice, there's a little bit extra even here. So it's small n minus capital N, but I guess that is what happens to you if you would put C and alpha to 1. But anyway, as I said, even though it looks ugly, it's actually quite natural. And what can we then prove? So after some cutoff, so at least 2 particles. If you have just 1, I mean, it's not an interesting system. If you have 2, it's maybe still not yet interesting. But we show that there's some number of particles after which the following result holds. So this N0, I don't know, think of it as 10, 8, whatever. I think we have some estimates, but I never remember what they look like. I don't think we actually compute it very well. But it's some number. It does depend on on three things. It depends on how you chose the parameters for your control. So C depends on initial data, you can think of like that. Alpha depends on how careful control you want to have. And N star is the maximal order of cumulants. So the more cumulants you want to have, the higher N0 might be. So if you want to look at 1,000 order cumulants, you might choose a fairly large N0. But other than that, we assume nothing about the initial data. It's a probability measure which is symmetrized, so it has to be symmetric on the sphere. It has to have a support on the sphere, but nothing more than that. Small n is something, so this is a collection of integers from 1 to n star, so anything up to order n star. T is the time, we are going forward in time, so it's non-negative. And this is what we are interested in, the cumulants of this. R is a collection of labels. We assume that the alpha C are such that the initial data satisfy the bounds above. Then these bounds still continue to hold. But not only do they continue to hold, they get better. So if you think of the original bound, I think it's the same one as the here without these three factors. That was the original one, roughly. I mean, not exactly the same, but that's more or less what you start with. And when time goes on, you let the system evolve. You end up, two things happens. This factor here, which was relating to alpha, it won't go away. You will have the smallest factor here for all times. This factor which goes to corresponded to C, I said that measures the degree of chaoticity of your state. This will decrease, and it will decrease with the same exponent. This 1/4 is not optimal. It's again a choice of convenience. This is more or less the same type. This is connected maybe to the gap, spectral gap which you saw before. It would be maybe closer to half, I guess. But in any way, it's some finite number, order 1, and this at times which are maximally log capital N, it will cancel out that one. And as soon as this factor here, the second factor, this is smaller than that, this here is bounded by 2. So it stops being important. And that's what we mean by generation of chaos here. So you wait, whatever initial data you have, even if it's totally deterministic, if you wait log capital N steps, you will end up with something where your cumulants are tiny, in the sense that every time you add a new random variable, you gain 1/n roughly extra. This result allows you to do other things as well. So we can study the equilibration also in terms of cumulants. So we know that the measures, at least if they have a density, they converge to the uniform density on the sphere. So therefore, you would expect that the cumulants, time-evolved cumulants, would converge to the cumulants of the uniform density. That's a kappa bar here. And indeed, that's also something we can prove. So we can show that the difference between these two guys is just the same thing as in the above, without the second factor 1. So these guys, in fact, go to 0 when t goes to infinity. So that's a sign of equilibration. So equilibration also happens roughly on the same time scale. So if the initial state is chaotic, so that was c equals 0, then the equilibration time is order 1. Otherwise, it's order log n. And equilibration time means that up to errors which are pretty small and n is large, the cumulants converge. What I find the most intriguing is that we also can say something about the kinetic theorem. So same initial data as before, and now we wait some time t0. That's actually an important step, by the way. So we have to wait a while. So don't look at the beginning. So it could be something totally non-chaotic. So don't stare at. Wait a little bit. The time you need to wait is nothing if you are already chaotic. Otherwise, it's something which is log capital N. It depends on the maximal order cumulants you want to see, and it depends on the C factor, which was the chaoticity of the initial state. So you have to wait this particular time, and after that, what will you do? You are not yet at equilibrium, by the way. That is not guaranteed. There is still non-trivial time evolution after this t0 waiting, most likely. No, it's a consequence of this result, in fact. So, but you have to wait. And why do you have to wait? You have to wait in order to measure the initial data for your Boltzmann distribution. Namely, what you do next, at the time t0, you take your first marginal. It doesn't matter, by the way, which one you take. It's exchangeable symmetric distribution. You pick one particle label, look at the marginal. This distribution is F0V. I'm not sure if it's actually, it could be a measure still. So with our initial data, this could still be a measure, although I'm not completely sure. It probably might be a density even. But anyway, let's assume it's a density. The notation assumes that it's a density. There is a measure version of the Boltzmann as well, but let's assume it's a density. So after T0, you measure the density for your marginal. And now it's with respect to Lebesgue on R, I believe. So there's a little bit of complication going on here. But anyway, you then take this F0, it's a function of R, and you solve the Boltzmann. That's the Kac equation, the Boltzmann-Kac equation I wrote to you before. Maybe some prefactors which are related to a different scaling Kac used in his derivation, but up to the overall constant on the right-hand side, it's the same equation you saw before. Okay, then do something to construct so-called, let's call them Boltzmann-Kac hierarchies. So let's do something fake and take your solution, ft here, construct a measure nu t from this, that's a measure on R, and take a product out of this. So this is n-fold, capital N-fold product of these measures. This is no longer a measure on the sphere, that's a measure on Rn then. This measure, it's a probability measure, it also has cumulants. These cumulants are here. So those are the cumulants of the hierarchy, which you get by solving Boltzmann and making a product, and then computing cumulants. You realize I'm cheating a little bit because most of these guys are 0. But anyway, that's what we do. And you measure how close they are to each other. So T0 was the time I needed to wait. These guys still are the original system. So these are really the cumulants of the original Kac model. Nothing has changed there. The only thing is changed that I measured for times capital T after T0. So this is capital T is, again, think of this equation starting at T0. That's the solution at time T, capital T after T0. Now you compare these two guys together. How close are they to each other? And the answer is that they are, when n is large, they remain always close to each other. And this result is uniform in capital T. So this shows that the solution to the Boltzmann yields a more or less perfect approximation to the statistics of your system for all times after T0. And that's good news for kinetic theory. I mean, of course, I should say as a caveat that that's too much to expect for any other models. But in this particular model, this is true. Boltzmann equation, this is really a perfect model for kinetic theory. Kinetic theory becomes essentially exact after time T0. I wanted to say a couple of words about the proofs. I see time is running out. I think I'm having something like 15 minutes. What I was planning to do is to show you how do we control these things. I need to rush a little bit, so let's just look at the salient points here. And we are using all these things which I mentioned in the proof. So the symmetricity of the measure is important for the proof. The mean field nature of the measure is important for the proof. And the conservation law is important for the proof. The way we are looking at this, it's rather complicated hierarchy. The nice thing about this is that it's a closed hierarchy. So if I look at order n cumulants, they only depend on order n or less cumulants. The evolution equation is highly nonlinear, though, so that's bad news. So it's a nonlinear but closed hierarchy. The conservation law allows us to sort of solve one particular problem relating to the fact that there cannot be no generation of chaos in the direction of the conservation law because it's constant, so it's a deterministic number. But in fact, it will help. This is something which we can do in the energy variables. And now the way to handle this thing, the complexity, is to simplify the hierarchy so that we only look at we use the exchangeability to sort of reduce it only to the question of how many different labels do you have. And when you look at the evolution equation, the real full one, these arrows show how the different cumulants interact with each other. So this arrow is so-called most important, what we call a break term. And when you look at the dependence between the cumulants, these arrows show it more or less as it is. And in fact, up to here, everything can be done using, well, ideas, standard ideas. Techniques are not standard. Let's say standard ideas from fixed point theory and stability of fixed points. What is important to realize is that there's at the bottom of this guy is the thing which has only, so this counts, all of these have n5, the small n equals 5. And the sequence tells you how many times that particular label is repeated. So the bottom one here is the one where there are no repetitions. And we indeed have to analyze separately the evolution of these guys. Fortunately for us, because of the conservation law, we can make the hierarchy of those guys to be closed as well. And then this is the one special thing about Kac model and energy variables, which allows us to do the analysis rather cleanly. If you look at the hierarchy, it has this particular structure. All of the cumulant hierarchies usually have this. There's a linear part which connects the linear operator connecting the different levels of the hierarchy to each other. And then there's this nonlinear part coming from the Wick polynomials, if you want to know where they are coming from. And the linear part in this model splits into two parts, where they behave nicely with respect to this partition label. Partition classifier, sorry. And the way they behave nicely is because there is a gap. So we look at this in the Banach space with this particular norm, where this, as I said, we are sort of interested in how small these cumulants are with respect to these weights which depend on alpha, and that's the norm then. So we look at the evolution, how small are these terms in the hierarchy in that particular norm. And generation chaos in terms of the norm can be written in this type of equation. I should maybe mention that this was not the typo, this n squared. That's partially our laziness and partially our, we don't know how to do better. So these estimates which I showed to you, they become rather horrible if n is small, n is large. They are good in capital N, but they become horrible in small n. Maybe a better, that's one place where the proof might have room for improvement. The key idea here is that these terms have an explicitly dissipative term. It's almost like -half times the cumulant on the left-hand side. So there's an exponential dissipation appearing in this hierarchy, and this is due to the sort of high stochasticity, I would say. In the other models, this is not so easy to identify. But that's behind the fact that we can really go to t going to infinity. So this will dominate this dissipation here. That's of course the hard part to prove, but we do prove it. It gets a bit complicated. I'm just flashing through these things so that you get an idea that it's not completely straightforward. It sounds easy, and it is easy if you know what you are doing, but there is some combinatorics involved. The part of the reason is that maybe some mystery. I mean, I said something which was probably not so clear. I told to you that the energy satisfier in hierarchy. That sounds strange, because if you look at what happens to energies when you rotate them, they do depend, or look like they depend on the V's as well. That's coming from the rotation. Fortunately, these terms will cancel out because our measure is symmetric. So all these V's will vanish. Anything which depends on V's will vanish, and indeed we do get a full hierarchy for the E's alone. You see the Wick polynomial generating function appearing here, and that's the full equation we are actually analyzing. It's harder to simplify this much more without going into horrible formulas. But the reason why I brought up the Wick polynomials are that even though this is a stochastic model, it's not the deterministic model at all. Nevertheless, when I look at the evolution of cumulants, these Wick polynomials naturally appear here as well. After this, combinatorics starts to become a bit cumbersome, as I said. We do need this formula to simplify it, and this is the outcome, as I said. The main simplification is that this V dependence here, which is still visible there, will drop out by the symmetry of the expectation. So because V is symmetric with a flip of its sign, odd moments vanish, and even moments you can write in terms of E's. That's really the trick what is going on here. Anyway, we have a closed hierarchy, explicit hierarchy for the energies. We write it. We identify the dissipative part. That's going to M, and we write the duomel, and then we look at fixed points. That part is what everybody else does. Sorry, no, I said wrong. No fixed points. That's the difference. Yes. We are not inverting this. That's another thing which is nice about this, because the nonlinear part doesn't need inverting. That's another thing which is crucial in this analysis. It only depends on strictly lower order cumulants. So this term is in fact a source term from the point of view of hierarchy. If you look at it level by level, not only is the hierarchy closed, but you can exponentiate. This M contains anything which depends on the same order, and the rest is strictly lower order, and therefore we can treat this as a source term. So our proof is not a fixed point argument, it's not a Banach fixed point at all, it's actually induction. So it's an induction argument in the bound which I gave to you. And here is the dissipative part. So this M is actually nicely dissipative. I think now we are going to technical details, and time is maybe running out, so let me leave some room for questions if there are any. So I said that our hypothesis was that cumulants are a nice way of measuring almost independence. So again, I should say that these cumulants, even at the uniform measure for fixed capital N, they are not zero. The conservation law, the fact that it's a measure on the sphere creates dependence. It's a tiny dependence if it's smaller the cumulant, but it's there. And in fact, we prove that the cumulants of the equilibrium measure have a similar bound, and then what we proved for the generic case. So in that case, you gain roughly 1 over capital N for each new label you add to the system. So even though they are not independent, the dependence from the sense of cumulants decreases. Every time you throw in a new label, variable with new label, you get a much smaller thing coming out. As I said, this was originally starting from analysis of more complicated systems like the non-linear Schrödinger equation. And that's what we are trying to do next. There are complications which I guess I don't want to talk about here and you don't want to hear. But the hierarchy is a bit more complex layer. In particular, it's not closed hierarchy, and the linear analysis is harder for that case. And there's no dissipation to help you. So this dissipative part for the argument was coming from stochasticity. That is not present for the nonlinear Schrödinger or Hamiltonian equations I've seen, at least not as strong. So the strong dissipativity was a product of the strong stochasticity. There's one case which we would like to understand better. That was Eric Carlin who heard this talk, an earlier version of this talk half a year ago, I guess it's already now. He pointed out that they have been studying a different version of the Katz model, where you allow the collision rates to depend on the velocity. So that's a natural change if you think of real particles. So the faster the billiard balls move, the more likely they are to collide with somebody, right? So there's a quantified version of this which Eric has studied. I guess it was with Bernd Wernberg. But what they saw there was the speed up of things. And indeed, based on what we discussed and what would be interesting to check is that in that case, will the generation of chaos time decrease from log capital N to 1? I mean, it's a bit unfortunate if you think about my Boltzmann result. I had to wait log capital N steps, then I start the Boltzmann, but that's order 1 evolution. And the Boltzmann drives me to essentially Gaussian in order 1 time. So most of my time is used to generate chaos then. Then after that, I'm at equilibrium. So for the Katz model, the times are roughly like that. That's chaos. Then there's Boltzmann. That's order 1. And after that, up to infinity, you are so close to equilibrium, you will not see anything. But in the other model, so this could be a feature of this velocity independent collision rates, and indeed the sort of the hypothesis is that if you look at the other model with more realistic collision rates, this time would also become order 1, and therefore that's more reasonable. So you have to wait mesoscopic time, let's say, then you generate chaos. After that, you can use the kinetic theory to check what happens. And if you are lucky, like we are lucky in the Katz case, you are already at equilibrium and nothing more happens. I should maybe say that this picture is known to be false for some other models, by the way. So kinetic theory is not perfect. It's known to be non-perfect in some cases, but it's surprisingly good. That's maybe my concluding lines here. In any case, so I'm happy to take questions if there are any, and if there are not, thank you for your attention. I can't hear any questions, but
yeah. So you took the assumption that your theta was uniform on the circle.
yes.
I guess if you move to, so this means that you are considering two-dimensional particle systems, right?
Well, I think I have one-dimensional actually, because the velocity is one-dimensional. So it's two particles colliding. So they are rotated. So you need to take two velocity vectors and then rotate. So if I'm in one dimension, then I end up with the two-dimensional rotations. And the uniform distribution could be important. I don't. If
Okay.
for instance, if you change it to something which is not symmetric under the flips, I think the energy hierarchy is no longer closed. At least, okay, so I don't know examples when it's not closed, but that's the case where we cannot see immediately that it's not
Okay,
closed.
so the distribution of theta is important.
Distribution of theta is somewhat important. So some properties are important, and in fact, you can think why. Take a distribution for the collisions which is delta. Then you realize that this is not generating chaos.
Okay, yeah. I was more thinking about like you take two random.
Okay, so if you take something which is symmetric in the sense that going forward and back has the same probability, so it's a symmetric under the flip of velocity, and it has density with respect to Lebesgue, then we probably would be back to business. The rates will depend on this, I believe. So something will change, but the main message probably will not. That's an interesting question, by the way. So I forgot to add it to the list of questions. So how does it depend on the rule how you choose the direction from after the collision? Yes.
Okay.
Or how you distribute the velocity, your new velocity between the particles, your energy between the particles. And again, a similar question in higher dimension. So this will be more complicated, this part.
Okay, thank you.
So, sometimes people use the spectral gap inequalities, logs of Lev inequalities to generate chaos or to analyze convergence to equilibrium in general. So,
yeah. So excellent question, and for that part, of course, I don't think we can say anything more. So I suspect that those techniques were behind the results I quoted here. So I think they are following this well-established entropy production estimates in this game, and that's the way you prove, for instance, the convergence to equilibrium. What else can I say about it? So we cannot add to that. And in fact, our equilibration result doesn't have anything new, except it says that if you look at small n particles only, it's much faster than what you would expect. So it's only everybody goes to the same place. So our result is just perfectly consistent with the fact that it goes to uniform. But it's really a question how fast.
Okay.
And I think the spectral gap result, I mean, it is a spectral gap result. So it says that if you look at all generality, all observables, all initial data, you cannot beat it. So the reason why we can beat it is that we project to the marginals with the small n variables.
Yeah, I have a question, Pablo from Buenos Aires.
Okay, hi.
How are you? Thank
Thanks,
you
how
for
are you?
the nice talk. Hard for us to understand, but very nice. So in the one-dimensional case, in the previous, in the usual rod or gas, there is no problem about your result, right? You have
so our result is I think it's exactly in the usual case. So well, there is this particular problem that there is, as far as I'm aware, there is no result about cumulants. So the surprising part was actually that the cumulants are so good at measuring independence. I was trying to find results about cumulants of the uniform measure, which would be as good as what we got. So to show for uniform measure that the cumulants gain an extra factor whenever you add a new label, even that I couldn't find. Maybe that was my laziness, I don't know. But anyway, from the point of view of results for full system answer is yes, it is the same result. This is the most well-studied system you can think of. It's really a question about how well do the cumulants do, how fast do they converge, and how well does the kinetic theory act. One thing I should maybe mention that these results I had for the kinetic theory, they are uniform in capital N and capital T. If you look at the usual scaling limits, you can never say anything more from times which are larger than kinetic. Of course, you would expect to be close to equilibrium, but it's hard to prove.
But if you start with independent velocities times 0, and your system is invariant by translations, you get the same, right?
Yeah, okay, but the system was started on the sphere, so this has a fixed energy initially. So when I talked about the Boltzmann-Kac result, so this tilde measure here is not a valid measure for my initial data.
Okay.
Because it doesn't live on the sphere, it's missing the constraint.
Okay.
So part of the difficulty in the cuts was exactly that, because you have to project it on the sphere, and then that will generate extra terms which you have to then deal with. So you take sort of like this F tilde, and then you project this on the sphere. That's how you construct the cuts initially.
Yeah, exactly.
Yeah.
Okay, thank you.
Okay, thanks.
Thank you for the talk. Very nice.
Thank you.
Well, if you don't have more talks, let's thank Jani one more time for this very interesting talk.
Thank you very much.
So thank you, Jani, for the talk.
Okay, the recording, I guess you can put it online.
I think so. They do automatically.
Okay, very good. Yeah, so if there's nothing else, I wish you a good evening.
Yes.
And let's talk later.